Hi all, welcome to tutorial video 5. This video covers user environment and exception handling, the first part of Lab 3. Before we start, please take a look at this summary. And Lab 3 is basically for creating user environment and making your JAWS run code in Ring 3. And you will mainly edit current env.c along with pmap.c, trapentry.s, syscall.c from kernel, and edit syscall.c and syscall.h from lib and inc, which are user level code for invoking system calls. And if you are suffering a weird infinite loop of execution of your JAWS, then please check if you are using the correct version of the QEMU. In this regard, if you are working on our OS2 server, then your path must include home/bin. If your path does not include that, then please add that, because we have our modified version of the QEMU at the home directory /bin/QEMU system i386. So one of the easy solution is you may use bash, because our .file script includes that for you, or you can do that by yourself. Or if you cannot resolve that problem, then please ping our TAs on Discord. And to start with Lab 3, you need to merge your Lab 2 to the branch, Lab 3 branch. So if you're on Lab 2 branch, then please check your git status, commit all changes, and then check out Lab 3, merge Lab 2, then start. And there could be some merge conflict, and if happened, please resolve that. And in case if you do not know how to resolve a merge conflict, then please consult to our TAs for help. Next, let's start with exercise 1. The exercise 1 is for allocating the ENVs array. And this array is for storing a metadata for user environment, and the allocation of this array can be done in a similar way what we do for the allocating array pages. So please refer to how you implemented that part in Lab 2, how you allocated pages using bootolog, and also how you map the pages to have a dual mapping for user and kernel for different privilege using bootmap region. And you will do the same thing for allocating ENVs with bootolog and use bootmap region to have a dual mapping. For example, enable read-write for kernel, but enabling just read permission for the user level. And if you finished your Lab 2 correctly, then you can finish this part easily with the 3 or 4 lines of code. But you will see that your implementation does not work even with the correct implementation for some cases, because there will be a weird memory error at this point. And this is because we use bootolog and bootmap region to allocate map ENVs. And then these are not marked as in use because we do not adjust pp-ref of them. And to avoid such a problem, please adjust your implementation for bootolog to reserve more pages for the in use. And especially for when it sets the next free for the first time, please put the +1 or plus 100 after the end. I think a +1 will be enough for the finishing up to Lab 4. And this will reserve additional space for the array ENVs. And next is about exercise 2. You need to implement the 6 functions in exercise 2, as we did in Lab 1 for exercise 1, and exercise 4 we implemented multiple functions. And as you did in that phase, please read the comments in the code thoroughly, and also the lab description thoroughly, to understand the requirement of the function correctly before starting implement. For example, env init asks you write a function for creating the env free list out of like an envs array. However, at there you need to build the list in specific order. The initial list should have the same order of the traversing element as the order of the array itself. Otherwise, you cannot pass the sum assertion check. So please be careful for reading, catching like this kind of the details and follow the guideline. And next is about the ENV setup VM. And this function is for setting up a new virtual memory space for environment, which is for process, and basically it allocates a new page directory to the environment. So we know that a process's virtual memory space can be defined as a page table and page directory, and to allocate the new virtual memory space, what we need to do is we need to create new page directory and tables. And in setting this up, setting the new page directory, because we will share the kernel part across the all environment, you will need to copy the entries from kernel page directory for the entries above the utop. And then the function will need to set like a ubpt, and you can do that by setting it as the physical address of the page directory. And in addition to these, please be careful to increase the ppref of the new page that you will use for allocating the page directory. And because the page alloc does not increment the ppref, you should increment the ppref before returning this function to mark that the newly allocated page for page directory is in use. And next function is region-alloc, and this function is for allocating virtual memory space for a certain size. So for an environment, it will allocate the virtual address starting at VA for a size length. And you can regard that this function is similar to bootmap region, but the different thing is that in bootmap region, it must be both virtually and physically contiguous. But in contrast, in region-alloc, the region is contiguous in virtually. However, the physical address that backs those virtually contiguous memory location does not have to be contiguous. And please use page lookup, page alloc, page insert wisely for implementing this function. And next is load icode. This function is for loading application code to ring 3 to the memory space of the environment. And one thing that you should be careful is that because we need to load the code and data of the application to the virtual memory space of the environment. But right now, we are using the virtual memory space of the kernel because what we are using is current pgdir. And the CR3 register of your CPU currently points to the physical address of the kernel page directory. And to access the virtual memory space of the environment, we need to set the page directory address of the environment to CR3. So we need to update CR3 register to make available make the access to the virtual memory space to an environment available to our code. And to do that, at the start of your implementation, you may include these 2 lines of the code to store the previous value of the CR3 register to prev CR3 variable by running the function rcr3, and you may regard this as a read CR3 function. And after running this code, you can and then like it will run the lcr3 for loading the address of the page directory of the environment. But at this moment, you should wrap it with PADDR because our CR3 register will only accept the physical address. After that, we can access the virtual memory space of the environment. And after enabling the access to the virtual address space for the environment, you need to load the program. And the user level programs in JAWS are written in ELF format, and so please revisit the background of the ELF header if you are unclear about this. And the header contains the information about how the program is loaded in the virtual memory space, so please refer to those information in the header, and you can load code and data of the application using memset and memcopy and regional log. And you need to allocate the virtual memory first to load the code and data by using memset and memcopy. And if you're unclear about how you can parse the ELF header, then please refer to how boot main function in boot/main.c read the ELF header and load the address. You can use the similar code. You can basically copy those code and then edit the code to match your situation. Then you can implement this part. And after finishing load of the code, before returning from load code, we need to put the previous page directory back to the CR3 because at the start we changed the CR3 register to point to our environment page directory. And you can do that by calling lcr3 with the previous cr3, the variable. And please make sure you run this before returning from load code, like this. And the next is ENV create. What it does is initialize a new environment and load the code. So please read the description and comment thoroughly, and use the functions such as envalog and load code to finish this function implementation. After that, you will implement the env run, the function which is for switching the execution from the kernel to user level. And please follow the command carefully and implement as it says. And this will finish the implementation for exercise 2. And for exercise 3, it says you need to read the chapter 6 of the Intel manual, but it's quite long, so you don't have to read it all, but please refer to the manual for that part or this table whenever you are not clear about how interrupt handling works. For example, to identify whether the interrupt has an error code or not, we can refer to this table for this column. And then, in exercise 4, by using the information whether or not having an error code for a certain interrupt vector, please implement the trap handlers per each interrupt. And if they do have error code, then please use trap handler. And if they do not have error code, then please use trap handler no EC. And for implementing all traps, please be focused on constructing the trap frame. And because CPU does not automatically store the DS, ES, and all general purpose registers, you need to push them all in the reverse order that is listed in a struct trap frame. So what you wish to do is push DS, push ES, and push all general purpose registers. And then please follow the guideline 1, 2, 3, 4 written in the exercise 4 for implementing the rest of the part, and you can refer to how you can implement the second part with this 3 lines of the assembly code. And in doing this, please refer to the detailed data structure of the struct trap frame and the push registers. And then in current trap.c, you need to implement the trap init function as part of the exercise 4. Please use the code in the command as a reference using of the setGate macro. And for example, to implement setting this kind of gate for the divide by zero error, then you can use the macro like this. And please do this for all kind of the interrupt exceptions that JOS need to handle. And in doing this, for breakpoint and system call, only for these two interrupt number, please set it be allowed for ring level 3, because those can be invoked from ring 3. And you can set that by the putting number 3 at the last argument of the a setGate macro. That indicates this is allowed for ring 3. And to get the page directory, please use the function rcr3, read cr3, and make sure that function returns the physical address of the current page directory. And to get the virtual address of it, you need to wrap it with kaddr. And how to set the page directory back to cr3. And you can use lcr3, load to cr3, and make sure that you supply the physical address of the target page directory. So if there's a virtual address, for example, environments page directory, then you should wrap it with the paddr to supply the physical address to lcr3. And the next is for another tip for running a specific user program. In Lab 3, JOS has several user programs to test your environment like these, and because you are required to write code for handling system call in user level, you might want to run the program separately to observe its execution and attach GDB for debugging purpose. To do that, you can run the command via our makefile script. And so if you run make program name nox, then it will run the program. For example, to run the program debug, then what you should run is make run-divzero-nox. And if you want to attach GDB on it, then you can add the -gdb at the end, make run-divzero-nox GDB, then it will wait for your GDB connection before running divzero. Like this. So if you run make divzero-nox, then it will boot your kernel, initialize the memory, virtual memory, and the environment, running the entire part of the lab 2 and the exercise 1 part of the lab 3, and then it will run the user program divzero. So it says there's a new environment and then runs, and it got trapped because it intentionally generates the divide by zero error as the program name says. And the next is for how you can apply debugging to this user program. And you can do this by the starting tracing with GDB from starting from the user execution. And you might be curious about where the user program starts. And you can do this easily by setting a breakpoint at the function env-pubtf. The reason why I recommend setting the breakpoint at there is we need to use iret instruction to switch from kernel to the user execution. And JOS calls JOS uses that iret instruction in the function env-pubtf. So you can set the breakpoint at that function and continue. And if you follow a few instructions with si, then you will meet the instruction iret, and the instruction right after executing iret, that's the starting point of the user program. And in debugging user program, it will miss the source code part in GDB. However, you can refer to the obj/user/program-name.asm, for example, debug.asm, to get semantics of the assembly code. And for next, I will demonstrate how you can apply debugging as the last part of this tutorial. So if you are getting to the this kind of console, then you can run tmux. Now I'm in the tmux, and let's say you want to use you want to run the debug program. Then what you can do is make run debug-0-nox. Then it will run the kernel and run entire lab 2 and a little bit of lab 3, and it will run the user program deb0, and internally that user program will generate the divide by 0 error, so just catches that. And then in case if you want to apply debugging, attach GDB on it, then what you can do is just attach -gdb, make run debug-0-nox GDB. And it waits for your connection from GDB. Then let's move to the another pane. So right now I'm running the make run debug-0-nox GDB on the window 0, and at window 1 I can attach GDB. And then let me set the breakpoint at ENV pop tf, and then let me reduce the size of the screen like this and continue. Then now our execution is stopped at the start of the ENV pop tf, and the assembly lines here shows the instruction. And we want to stop at the exactly at the point of the instruction of the iret. And to do that, we can follow the instruction with si step into. Then it will move one si, then move one more si, one more, until it meets iret. Now we are at the iret instruction. And after running this instruction, it will our CPU will start the ring 3 execution. And let's see how it actually works. And then right now, the CS register of the current execution is, the value of the CS register is 8, and 8 means 1000 in binary, and the last 2 digit of that one is 0. So we are in ring 0. Then take a look at what will happen if I run si. Now we are at the instruction pointer 800020, and this is actually the start point, the entry point of the user program, which is written in the ELF header of the deb0. And please check the CS register, and now it says it is 0x1b, and b is, so 1b is 16 plus 11, so the value is 27, and the 27 in binary is something like this, and the last 2 digit of the CS register value is 3. So now we are in ring 3. But when you get to the user code, then you will lose the source code part of the user program. And to learn about the semantics of this kind of assembly, then you can open obj user deb0.asm as a reference. Then you can see that the 800020 is the start, and you can see a sum of the additional information written in the assembly as we did it for like the checking the implementation for the like a bootloader or some other like a kernel part. So please use like this kind of the information and this GDB and this kind of the script tool that you can attach GDB to specific user program when you debug your like implementation for lab 3. And this is the end of the tutorial video, and on next Tuesday we will have another video for guide you to like its second part of the lab 3. Thank you and have a nice day.